Okay, so today we start doing Fourier series. So we are still doing Fourier series, and this will take us some time. But let's look at functions of any period. So remember, what we did so far is functions of period 2 pi. So we've seen all the integrals going from negative pi to pi. Now let's see if we have a function, so let f be periodic of period not 2 pi but 2l. So l here is a certain number. L is any positive number, okay? So now what we want to look at is a function that repeats itself every 2l, and usually, like the block, our basic block is minus l to l. So imagine you have a function like this, for example, and then this function repeats. So when it repeats, clearly it will have this form like this, and copy paste, you know, the idea, and something like this, and so on. Okay, so this is a periodic function of period 2l. So the 2l in this graph is this length here. We want to show or to find or to see what the Fourier series of this function looks like. If we go back a little for the Fourier series of a function that's periodic of period 2 pi, if you remember, the a node, the an, the bn, all of them have some integrals from negative pi to pi. So I think now, because my period is 2l instead of having 2 pi, we expect this integral to be from negative l to l. But let's see some details. So why is it minus l to l? And I like here to remind you that I said once in one of the previous lectures that once we accomplish the minus pi to pi, the 2 pi period, from that we can look at any other period. So let's see why we can find it for any period if we understand the 2 pi period. The idea is this. So you have a function of period 2l, okay? We define a new function, call it gx, that's equal to something, f of something, okay? But I want this function. So this parentheses are empty because I want to construct the function g so that the period, so then g is periodic, this is what I want, of period 2 pi. So now I want you to tell me what we should write inside f so that the new function has period 2 pi. To guide you through the idea, remember we had one property here, just to remind you, if f has period 2l. Remember, we had some property, for example, just to show you what happens in general. If you have f of 2lx, what is the new period? If you remember, we divide the old period by the coefficient of x, right? For example, let's look at the easy examples. For example, sine 2x, what's the period? You ask, what is the period of sine x? It's 2 pi. You divide it by the coefficient of x, you get pi. So now, what is the original period for f? It's 2l. You divide it by the coefficient of x, which is 2l. That gives you what? That gives you, so the new period is 2l over 2l, which is 1, right? Now, I don't want it 1. I want the period to be 2 pi. So the idea is I divide this by 2 pi. So now what's the new period? It's like this. So f has period 2l, you divide by the coefficient of x, which is 2l over 2 pi. The 2l is cancelled, and now you get 2 pi. So the idea, we define g to be f of what? F of l over pi x. So this is our definition. This is our definition for g. Then the function g has the period 2 pi. If it has the period 2 pi, then you know what's going on, right? Because then you have everything about the Fourier series of g. So now what is, so now we ask, what is the Fourier series of g. This is the question. Okay, we move. So the Fourier series of g has the form a naught plus the sum, and from 1 to infinity, an cosine what? An x, right? Plus bn sine an x, right? But what is a naught? A naught is 1 over 2 pi, yes, because now we're dealing with g, right? It's the integral from negative pi to pi, g of x times, just g of x. Of course, you can say times cosine 0x, but we never write that. Then what's the an? It's 1 over pi, integral minus pi to pi, g of x cosine an x, and the bn is 1 over pi, integral minus pi to pi, g of x sine an x. We know all of this, right? Okay. So we found the Fourier series of g, but that's not what we want, right? Because my original function is f. I'm looking for the Fourier series of the function f. But as an intermediate step, we constructed a new function called g. G has properties that we are familiar with, period is 2 pi, everything we know about it. So now, once we have this for g, now we move to f. So let's see what happens. Okay, let's see what happens. So the idea is a naught is 1 over 2 pi, integral minus pi to pi, g of x dx, right? Which is 1 over 2 pi, fine, integral minus pi to pi. Now the question is, what is g of x? G of x, we have it here, right? So it's f of L over pi x dx. But this f of L over pi, this doesn't look so nice. So the idea, let's get rid of L over pi. I don't want to see L over pi x. So what I'm going to do is to substitute L over pi x as t, for example. So the x is pi over lt, and the dx is pi over L. And of course, you need to change the limits, right? So you say this is 1 over 2 pi, fine, integral. What are the limits? When x is negative pi, the t is negative L. When x is pi, you just substitute into your substitution, you get L. What is f of? You substituted it as t. What's dx? It's pi over L, right? dt. Sorry, here we have dt. So now, when you look at this, the pi is cancelled. And what's left? You just have 1 over 2L, integral from negative L to L, f of t dt. Very nice. Very nice, yes. So the a naught, this is the summary. So the a naught has this formula. But this is very, very similar to the original a naught here when the period is 2 pi. So when you compare the new form to the old form, we expected this from the beginning. When the period was 2 pi, we had 1 over 2 pi. Now the period is 2L, we have it 1 over 2L. When the period was 2 pi, we have the limits negative pi to pi, now we have them negative L to L. Okay, so now the idea, when you look at G, this is the Fourier series. So it's like saying, it's like G of x is a naught plus the sum from 1 to infinity, an cosine nx plus bn sine x, right? And please, what do we mean? This is like the first time I use this notation. This is just to say the Fourier series of g is equal to this. Okay, sometimes we write this, sometimes we write that. But I like to use this notation in this example because now I want to say, okay, what is g of x? So f of what? L over pi x is this thing. Right? Just copying that line. But this is f of L over pi x. So again, I look at this and let's change it to t. So if we substitute, but please, this is not like a substitution in an integral. I just want to replace L over pi x. I want to replace it by t. So if you do this, then what you get is that f of t is this. So we're saying that the Fourier series of t is a node plus the sum, and from 1 to infinity for an cosine n. What is x? What is x? It's pi over L. So n pi over LT plus, it seems I need more space, so let me write it in a new line. So a node plus the sum from 1 to infinity an cosine n x. I'm copying this, but I replace x by pi over LT, right? Plus bn sine n pi over LT. And where? What is a node? We found it. A node was this. It's 1 over 2L integral minus L to L f of what? F of t dt. Okay, what is an? an has this formula. But if you do the same analysis like this, so if you write an is equal to this, and you substitute L over pi x equals t, what you get is so what you get is 1 over, don't worry, it's very similar. So what is the an when the period was 2 pi? It's 1 over pi. Now it becomes 1 over L. It was from negative pi to pi. It becomes from negative L to L. F of t, and the same thing as you had in the Fourier series, so it will be cosine m pi over LT dt, and the Bn is very similar to what we did, sine n pi over LT dt. So this is the Fourier series of the function f when it has the period 2L. Again, it's very similar. It's very similar to the Fourier series when the function has period 2 pi, and it's very clear that it's very similar. We obtained it from that case. It's very easy to memorize. There's no big difference. We need to notice that when, for example, when the period is 2 pi, that means the L is pi. So if you substitute, for example, the L here pi, then the pi gets cancelled and you get back to the original form. The same into here, if you substitute the L as pi, you get back to the original form. Okay, so these observations, I think, are very clear. Okay, so starting now, I will start dealing with the Fourier series of a general function, okay? A function of any period. We can solve a simple example. So as an example, let's find the Fourier series of, let's look at the function, for example, negative 1 to 1. I want to look at this function, okay? Of course, extended periodically. So what do we mean by extended periodically? That means, okay, this is the basic block, but then copy paste this black block to get a periodic function. Now it's very clear that the equation of this line and the equation of this line, what is the equation of the left line? The left line is y equals x plus 1. The right is y equals 1 minus x. So basically, what is my function? What is my function? My function is x plus 1 when minus 1 is less than x less than 0, and 1 minus x when x is between 0 and 1. Again, extended periodically. Okay, so now the period is 2, not 2 pi. So here the period is 2. That means what's the L? In our notation, we use the period is 2L. Okay, so if the period is 2, that means the L is 1. And then you can just proceed computing these integrals. So the other observation is that f is even. So when f is even, what's Bn? Bn is 0. Again, we will have one lecture for these even and odd stuff. We will have it in details. Then what's the A node? The A node is 1 over, previously it was 1 over 2 pi, now it's 1 over 2L, but the L is 1. The integral from negative L to L, f of t from negative 1 to L, f of t dt. But again, because f is even, I can replace the integral from negative 1 to 1 by double the integral from 0 to 1. So the 2 is cancelled, and you just get the integral from 0 to 1, 1 minus t dt. Of course, it's irrelevant. Is it 1 minus t dt or 1 minus x dx? It's the same thing. You get the same answer. And what's this? It's 1 minus half, which is half. So the A node is half. Then what is the AN? It was 1 over pi. Now it is 1 over L, which is 1. It was from negative pi to pi. Now it's from negative 1 to 1. F of t cosine n pi, don't forget this, n pi over L t dt. Again, because the f is even, the cosine is even, their product is even, so you get 2 from 0 to 1. What is f of t? It's 1 minus t cosine n pi t dt. This is, of course, integration by parts, so we need to do it as an integration by parts. Let's do it here. So the u, the dv, the u is 1 minus t, the dv is cosine n pi t, differentiate, integrate, then differentiate again, and integrate again, right? So this is negative cosine n pi t over n square pi square. Then you have this, 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 plus, minus, plus, okay? I think I don't need to put too much effort again to explain why I'm not writing the sign, because if you write the sign and you plug the limits, you will get 0. So I'm not writing them. So basically what's left is the second term. So minus with minus with minus, that's minus cosine n pi t over n square pi square, and the limits are from 0 to 1. So if you substitute, this is negative 2 over n square pi square, cosine, when you substitute the 1 you get n pi, minus when you substitute the 0 you get 1, so this is negative 2 n square pi square, cosine n pi is negative 1 to the n minus 1. I think we saw this idea before. So now negative 1 to the n has two possible values. It could be 1 or negative 1 depending on whether n is odd or even. So this is negative 2 over n squared pi square times, when n is even, you get minus 1 to the even is 1, minus 1 is 0. When n is odd, minus 1 to the 1 is minus 1, so you get minus 2. So basically this is 0 when n is even, and it will be 4 over n squared pi square when n is odd. So this is the an. So now we are ready to write the Fourier series of f. So what's the Fourier series of f in terms of t or x? Again, it doesn't matter. The a node was half plus the sum from 1 to infinity, the an and the bn. The bn, of course, is 0. We found it here. This is it. So now we just need to deal with the an. The an, it runs only over odd indices. So I'm writing here n is odd because the even ones are zeros. 4 over n squared pi square cosine n pi over L, which is 1 t, right? We've seen this idea many times. So now I want to remove this condition, n is odd. So I replace, so this is 4 over pi squared times, we replace every n by 2n minus 1 times cosine 2n minus 1 pi t. Okay, so this is, I think it's better to make this looks, so this is a 4, and this is cosine, sorry, I forgot, okay, cosine 2n minus 1 pi t. Okay, so this is the Fourier series. Okay, so we just replace the n as an odd number by 2n minus 1. This is the Fourier series of what? Of this function. This function is usually called, sometimes we call it rectangular wave, sometimes, triangular wave. We've seen the rectangular wave before. And that's it. Yes, this is the Fourier series if the function has period other than 2 pi. Do we still have like the same Dirichlet, the condition, if you remember, that the Fourier series of the function is equal to f of t plus f of t minus over 2? Yes, we still have it. So we can still apply the same formulas. We'll do this in more details in next examples. So let's delete this just to make things consistent.